In this video, we're going to look at another way to solve quadratic equations. In particular, we're going to solve quadratic equations by factoring. Now remember, we've already solved quadratic equations using the square root property. For example, equations like x squared minus 3 equal to 7. That is a quadratic equation because a quadratic equation is an equation with the highest power on the variable as a 2. And so what we would do here is get the squared piece by itself by adding 3 to both sides. When we do that, that isolates the square and gives us x squared equal to 10. And then once we get the squared piece by itself, then we can square root both sides using the square root property, which gives us the square root of x squared equal to plus or minus the square root of 10. And then the square root of x squared simplifies to x, and the square root of 10 doesn't really simplify. So we have that x equals plus or minus the square root of 10. So that's solving by the square root property. You get the squared piece by itself on one side of the equation. And then you square root both sides, making sure to remember to plus or minus the side that's a number. That's an actual number. So we're going to look at a different method now using factoring to solve quadratic equations. Now, the reason why we need a different method is because the square root property does not work well for all equations. So we have to develop some different techniques for solving equations. Let's look at an example of a quadratic equation where the square root property won't work. Let's say we have x squared plus 3x equal to 4. Now our strategy with the square root property is to get the squared term or the squared piece by itself. In this problem, that would mean subtracting 3x from both sides. And when we do that, on the left we're left with x squared. On the right, those are not like terms. So we have minus 3x plus 4. Or you could write 4 minus 3x, it doesn't matter. So we've gotten it so that we have just the squared term on the left side of the equation. So now we can square root both sides. That gives us the square root of x squared on the left, and then on the right we have plus or minus the square root of negative 3x plus 4. So on the left there, that simplifies to an x. On the right, that doesn't really simplify any. Now it may look like we've solved for x like we did in the previous problem, because we have an x by itself over here, and that equals all of this stuff. But the problem with that is that this stuff on the right still includes an x, so we've not isolated x's. We've still got multiple x's going on, so we've not solved x to be equal to just a number. And so what we've done is trapped this extra x under a square root. And the only way to get it out from under that square root at this point would be to square both sides of the equation, because that's how we eliminate square roots. But if I squared both sides of the equation, that would just bring me back to what I had up here. And I would be stuck in this cycle where I'm either stuck with a squared on one side of the equation or an x being square rooted on the other side of the equation. So the square root property isn't going to work in this particular equation, and the reason why is because we have both a squared term and we have x as a linear term as well. We have two separate x's. We can't combine those by combining like terms, and we can't manipulate the equation in some way where those where we can square root this x squared to get rid of the square on that. That's just going to result in having a square root, an x under the square root on the other side of the equation. So it becomes this cycle where we go back and forth between these two scenarios, and we can't get the x's together to get them by themselves equal to a number. So in order to solve this conundrum, we're going to resort to factoring. And that'll allow us to manipulate the equation in such a way to get x's by themselves equal to a number. Now, before we jump into actually solving one of these equations using factoring, what I want to do is kind of explain the logic behind why we can get away with the techniques that we're going to be using. So the idea here is we're going to exploit some properties of the number 0 when it shows up in an equation. To see how this works, think about 6 times 0. What does that equal? Well, 6 times 0 equals 0. Or 0 times 364. What does that equal? Well, that equals 0. So really you can take any number, we'll represent any number by an x, and multiply it times 0, and we know that that equals 0. We don't have to know what this mysterious number is over here. Regardless of what a number is, when you multiply it by 0, you're going to get a 0. Now here's, to kind of flip the logic on its head, let's consider we don't know what either number is. So we have an a and we have a b. Those are both mysterious numbers. We don't know what they are. But what we do know is that they equal 0. So if we have a product a times b equal to 0, then what could we say? Well, if a times b equals 0, then it has to be true that a or b is 0. So if a times b equals 0, then a equals 0 or b equals 0. And in math, when we use the or, a math or is more like an and or. So it's also possible that they both equal 0. This idea is called the zero factor property. So they're factors because they're being multiplied. A and b are being multiplied. If they equal 0, then at least one of those factors has to equal 0, and that's the zero factor property. So what we're going to do when we're using factoring to solve is use this zero factor property to allow us to get away with breaking the equation apart. Let's see what that looks like. Let's say we have the equation x squared plus 3x minus 10, and that equals 0. Now, when you look at this, because we have worked on factoring so much, you may notice that, hey, that looks like something I know how to factor. And sure enough it is, because we're working on solving by factoring. But that's not why we're going to factor it. That's kind of a contrived logic. The reason why we're going to factor it goes back to the idea of if I try to get the x squared piece by itself on one side of the equation, I would end up with an x term on the other side of the equation. So if I use the square root property, that would lock that x term underneath the square root, which doesn't allow me to solve for my x. So we need a different method. Remember, when we're solving, we are undoing what's happening. Now, we can think of what's happening over here on the left side of the equation in a more complicated sense of there's some fancy multiplication happening there, because we saw that these trinomials come from multiplying two binomials, and so by factoring we are undoing multiplication, just a lot more complicated multiplication than what we were doing when we were just solving linear equations. So we're going to undo that multiplication by factoring. If I factor what I have there on the left, it's going to be x plus 5 quantity times x minus 2 quantity. Now, we want to make sure that we keep this as an equation. Sometimes we get too focused on the factoring and we turn these equations into just factoring problems and lose the essence of the problem. So it's an equation, so we copy down that equals 0. So what I have here is, we've talked about when you have parentheses around something that groups an expression and says, think of this all as one number or one value or object. So basically I have a yellow blob being multiplied times a green blob. But I can actually think of that as my A times b, right? That's a value. X plus 5 is a mysterious value, just like a is a mysterious value. And I can say that a times b equals 0. And this is where our zero factor property comes into play. If a times b equals 0, then either a or b equals 0. So what that means with my equation is that I can say x plus 5 equals 0, or x minus 2 equals 0. One of those guys has to be equal to 0. It could be both of them, but at least one of them has to equal 0. And so what we've done is we've undone the multiplication, and using the zero factor property have been able to logically break the equation into two mini equations. And the beauty of those two mini equations is that I can solve that guy. That's just a basic linear equation. I can solve the first one by subtracting 5 from both sides. I can solve the second one by adding 2 to both sides. So we've broken it apart and gotten down to something that we have techniques to work on. And that's kind of the essence of our solving strategies, is to whittle it down to simpler and simpler equations that we can then solve using the more elementary level techniques that we've learned. And by elementary, I don't mean like elementary school, I mean like the first techniques that we've learned. So with that first one, I'm going to subtract 5 from both sides. That gives me x equal to a negative 5. With the second one, I'll add 2 to both sides, and that'll give me x equal to 2. So x equal to negative 5 or x equal to a 2. Now this both of those are solutions. The or doesn't mean you get to choose one. They're both considered solutions. So, and remember what a solution is. That means I can take this negative 5 and I can substitute it in for my x's in the original equation, and that'll compute out to make a true statement for the equation. It'll satisfy the equation. I could also take my positive 2 and put it in for both x's, and that'll make a true statement with the equation. And both of those work. So they're both solutions, and we can consider them together the solution set. It's not one or the other, you're not choosing. So, or in mathematics is a more positive or, where we're leaving our options open. It could be one, it could be the other, or it could be both. But we keep all our options that work. So that's solving that equation. Let's look at some other ones. This is just the general idea of solving by factoring. Now we've learned different factoring methods, so when you're solving by factoring, any of those methods are on the table that you might need to use. So here we factored a trinomial, but you might in an equation end up with other types of factoring that you need to do. To see that, let's look at this next example. Let's say we have 2x squared plus 20 equal to a negative 14x. Now one of the things we didn't have to do in our last example, we're going to need to do in this example. Remember that when we're solving these, we're using the zero factor property to get away with breaking it down the way we are. And so when you see directions that are solved by factoring, you can essentially add on the unspoken directions using the zero factor property. So when we're going to solve by factoring, we're always going to be using the zero factor property. And what that means is we need to have one side of the equation equal to 0. For the zero factor property to be true, it's going to be some things multiplied together equal to 0. And so it has to equal 0. Now that equals 0 could be on the left or right, but a product must equal 0. So with that, what that means is over here, we need to get either the right side or the left side down to 0. Since the right side has fewer terms, I'm going to work with the right side, and I want to get it to be 0. It's currently a negative 14x, so to get it up to 0, I need to add 14x. But whatever I do to one side of the equation, I have to do on the other, so I'm going to add 14x on the other side. Now we have to be careful here. On the on the right, that's just going to go to 0. That's by design. But on the left, this 14x, there's not any like terms here. And when we're told to add, we want to actually add something. But here, it's actually not possible. We can't literally add, so we're just going to write it out as an addition problem. So that's going to give me 2x squared plus 14x plus 20. Notice I kind of nestled that 14x in between the two terms that I already had. My motivation for doing that is I'm thinking in terms of factoring. And I can tell, since none of the like terms are going to combine, that what I'm going to be factoring is a trinomial. And to factor a trinomial, I need it in descending order. So I kind of just went straight there to putting it into descending order, because that's the configuration I need it to be in to think through my factoring process. So now that I have it written so that it equals 0, I'm going to go into my factoring questions. The oftentimes forgotten but first question we always want to ask when we're looking at a factoring problem is, does it have a GCF? In this case, it does have a GCF. Every term in this on the left side is divisible by 2 or divisible by 2. When I factor that 2 out, I'm left with the 2 outside the parentheses as my GCF, and then inside the parentheses I have x squared plus 7x plus 10. And now what I want to do is factor the trinomial that's left inside the parentheses, or try to. This particular trinomial factors as x plus 5 times x plus 2. And notice, even though I didn't use it to make my factoring decisions, I still copied down my GCF of 2. That needs to stay with us. So then, now what I have is I have stuff factored, and this is a little different than the explicit, and then how we started out with the zero factor property. Here what we have is 3 factors. 2 is a factor, x plus 5 is a factor, and x plus 2 is a factor. But logically speaking, our zero factor property can be applied up to any number of factors. If a times b, I don't know why I wrote that out of order. If a times c times b, if all of that multiplies together to give us 0, then we can, one of those has to be 0. So we can set each one of those factors equal to 0. So back to the equation, what that tells us is that we can say that 2 equals 0, or x plus 5 equal to 0, or x plus 2 equal to 0. Now here, this might be bugging you a little bit, the 2 equal to 0. I'm actually going to not talk about it just to kind of let it stew with you a little bit. I want to start by talking about the other two that are like what we saw in the previous example. So with the x plus 5 equal to 0, we can subtract 5 from both sides, and that gives us that x equal to negative 5. And then with the x plus 2 equal to 0, we can subtract 2 from both sides, and that's going to give us x equal to a negative 2. So those are great options. So now I'll go back to this guy. Now I'm not going to tell you that this equation tells us that that 2 equals 0. We're not going to do that. What this emphasizes the beauty of the word or. At least one of these 3 factors, before we broke it apart into the mini equations, at least one of those has to be 0. Well, we found values for x that would allow 2 of them to be 0. And what that means is we don't have to stick with this as true. Or gives us options, and so we can throw that out because 2 does not equal 0. Only one of the 3 has to equal 0 for our zero factor property to hold true. So what we'll do is we'll throw out the one that's nonsense, but I'll keep both of the other 2. So x equals to negative 5 or x equals to negative 2. And those give me values that I can plug into the variables in my original equation to produce a true statement. Alright, so that's the general idea of solving by factoring. If you're given a quadratic equation that has both an x squared term and an x term, we can't use our square root property. So we're going to resort to factoring. In order to use the zero factor property, we need to first get it equal to 0. Then we factor the non-zero side, set each one of those factors equal to 0, and solve the mini equations. And those solutions to the mini equations would be solutions to the original equation. Go ahead and give some of these a try and see how you fare.